Today is Monday, January the 31st, 2011. I'm going to document for you here a old Fisher 800B, made in about 1962, I believe. Just want to show you some changes that's been made to it so we can make some measurements. First of all, these capacitors have been replaced. These are the ones from the 12AX7s that feed the 7591s. They're just historically always bad. There may be some exceptions. I've also added some test points right here, here, and here, if you can see them. 4 test points and a 10 ohm resistors across from the cathode to ground of each 7591. So it does 2 things. It protects the output transformer in case there's a short in the tubes, and it also allows us to measure cathode current. So the test point right here, if you can see, this blue wire is hooked right here to the cathode. It's that way on each of the tubes. Other modifications is I added a switch right here. You'll be able to see from the top when I turn it over, so we can switch between the 5.6K resistor and another recommended 2.7K, so we can vary the voltage, the bias voltage, from about minus 15 to minus 20. It's one recommendation that I see out on the internet, and I think it's not bad. It allows us to run the tubes at a much lower cathode current and a lot cooler. And the purpose of this, one of the purposes of this video, is to document the differences, if there are any differences, between performance at a more negative, a higher voltage on the cathode, on the grids, a more negative bias voltage, the minus 15 versus the minus 20. We're going to document any differences. I've also added another capacitor in here. All of these old CAN capacitors, as you'll see from the top, are original, and they tend to open up or deteriorate over time. And as long as they don't short, you can leave them in there. Sometimes it's you have to replace them, especially if they do short. I've replaced this capacitor here. I think that was 100 microfarad. That's in the bias circuit. Other than that, oh yeah, I had to change the bias bridge rectifier right here. The old one that was in there, made by Siemens, was completely defective. This is a little one that you can buy in many different places. Other than that, the old amplifier, the old receiver, is pretty much stock. I'm going to turn it over, and we'll look at it from the other side. There are a couple of other things we want to do before we turn it over. We want to measure the bias voltages, and for the record, we're going to be measuring them here on a digital meter. There we go. Now we can see it at the right at the grid. I'm going to put the test point right there. There's one bias voltage, minus 15.8. Now I'm going to flip the switch. Right there. Now we have minus 19.6 with an input voltage of 120. We're going to run everything at 120. We're going to test it like that. This is for the documentation. For our plate voltage, the plate voltage happens to be 415, and the screen voltage is 386 or so. You can see that. Now, the schematics made by Fisher show right here minus 14.7 volts on the grids, old designs, and the RCA tube manual shows here push-pull class AB1 amplifier, 350 volts at about minus 15.5, and at 450 about minus 21. So we're running right in the middle of that, about 400 volts. So somewhere in the minus 18 volt range might be optimum for fixed bias. Okay, now we've got our measurements made. Let's turn it over. Now that we have it turned over, it's always fun to turn this thing over. These little dial cords are always a challenge, one on each side. It's very heavy too. Got to be really careful. Here are these cathode test points for each tube, and here's the switch that changes that bias resistor from a 5.6K to a 2.7. At 2.7K we get minus 19.7 or thereabouts, and the original resistor gives it about minus 15.9, subject to a little bit of line variation sometimes. What we're going to be doing is driving both channels at once with a Tektronix SG505 low distortion oscillator. We'll be watching its sine wave distortion. We can read its distortion right here on the this is an AA501 distortion analyzer. Voltmeter, which we'll be measuring across 8 ohms. Our 8 ohm loads are down here. We switch just the output here. This is what feeds all the equipment, but our 8 ohm load is hooked up through here. We also watch it on an oscilloscope, and we're also going to see a harmonic profile of it from an old Hewlett-Packard 3580A spectrum analyzer. Okay, first thing we want to do, there is a couple of more preliminary things here. The tubes that are in it, these two right here are old vintage tubes branded Macintosh and made by Sylvania. This is an RCA and this is a GE. And the reason I selected them like that and put them in that order is because when I test them on an old TV7DU meter for the tubes, I get a reading of 62 with a minimum of 36. So I get a 62, 62, 61, and 60. So my tubes, each channel is as balanced as I can reasonably get it. The 12EX7 driving it, one channel is, one triode is 44 and the other one is 44, so these are perfectly balanced, 48 and 48. I put the stronger one over here on purpose, because these are the weaker tubes. I put the little bit weaker one, 12EX7 over here driving the right channel, as these are the stronger tubes. Okay, now next, and this is one of the important things about changing the bias voltage, is we're going to measure the cathode voltage, which is actually going to allow us to determine the cathode current. So what I've got to do here is get this connected to one at a time. We'll plug it in. We'll measure the cathode current. Okay, that's 285 millivolts across 10 ohms. So that's 28.5 milliamps of cathode current. So we want to record that too. We'll call that 28, and we'll make a note of it right there. The next one is 31 milliamps. Remember, this is millivolts across 10 ohms. The next one is 16.8, so we'll call it 17. See, these tubes are a bit weaker, even though they measure the same on the old TV7DU. We don't get the same amount of cathode current, and this one measures 13. This is at the minus 19.7 volt switch range, so our cathode currents are fairly low right now. Now I'm going to switch it, and then we're just going to go back through again, like leaving it where it is. Now it's up to 23, so I'm going to write it over here, 23. This is with minus 20. This is minus 15 on the grids. The next one is 31. The next one is 50 milliamps. And the last one is 45 milliamps. So there we have them. These are our more negative voltages right here. These are at less negative voltage, so we have quite a bit more cathode current, which is going to make them run hotter. Now we're going to see what the performance is. We've got the old receiver on a turntable. Let me turn it around here so you can see the front. Yeah, it's a beauty. It's actually quite nice shape. Everything is set to normal. All of our switches are down. All we're going to do is vary the volume control. Loudness control is off. And I've got both inputs going into auxiliary. And here's our outputs right here at 8 ohms. So here we go. Let's see what it does. This is at the minus 15 volts, which is actually the more recommended voltage. We're going to test it at about 1%. 1% seems to always be a pretty good place to start. We'll watch the sine wave for clipping. Whoops, see there, we're overdriving it. They're knocking the top off. We have to be looking at the left channel. There it is, about 1.7%. Try to keep it right at about a 1% or so. It's really touchy. Okay, so we got 11 volts at 1%. There's our harmonics being generated by it. We got quite a few. This is our fundamental frequency, second, third, fourth, fifth, sixth harmonic. Not especially good, but that's the way it is. So we got about 11 volts at 1%. So our power is across 8 ohms is 11 squared divided by 8, which is 15 watts. That's about what it does with the weaker tubes. Let's go to the stronger tubes here. Do that by switching here. There's our sine wave. And we got less harmonic distortion. Now, our distortion went up ever so slightly, but not much. Still just a little over 1% at 12.4 volts. And 12.4 squared 8 divide is 19 watts. So that's about what it does at the with original circuitry. Now let's get back over here and switch it between the two. We're going to look at the right. We're going to leave it on the right channel for right now, and I'm just going to flip the switch. Okay, our distortion dropped and our power dropped slightly. Go back the other way. This is the minus 15. A little bit more power, a little bit more distortion. That's a minus 20. A little bit less distortion, a little bit less power. Here's our sine wave, back and forth. Minus 15, minus 20. You can see it grow ever so slightly there. Minus 15, it'll drop slightly here. Minus 20. Here's our harmonic profile. This is at minus 20, minus 15. It's a little bit higher. That's on our right channel. That's on our best tubes. So it's performing virtually the same. It's hard to measure unless you're using some very sophisticated equipment like we are here. You're not ever going to hear the difference, or you're not going to see the difference on an oscilloscope. Now let's go to our weaker tubes, which is our left channel. And I did notice some earlier when I was tinkering with this. Okay, we got lower distortion, lower output. This is at the minus 15. Now let's go to minus 20. Distortion went way up. That's kind of hard to understand, isn't it? But it's true. I've measured this quite a number of times. With the weaker tubes on minus 20 volts, the distortion goes up considerably. There it is with the minus 20. There's the minus 15. Okay, there's the minus 15. Let's look at the harmonics that generate in minus 20. Ooh, not good. The weaker tubes just don't perform very well. And actually, you can even see the anomaly here. This is minus 15. That's quite a nice looking sine wave, but you'll see some wrinkles occur right in here, right there. It's not as good as it was a while ago, and that one right there really tells the story. That's its harmonic profile. Here's its second. This is a fundamental. Here's the second harmonic. Here's the third. Third went way up. So there we go. Now you can draw your own conclusions of where you want to run it. Whether you want to run your amplifier with the original bias voltage, or whether you want to run it at a more negative bias voltage, which is going to make your tubes run a lot cooler and extend the life of them. But how they perform, it's kind of hard to predict, isn't it? It's pretty amazing that these two all these are vintage tubes. None of them are new. I don't have any new ones. If I did, I'd test them too. I have had new ones in the past, but they weren't mine. I borrowed them, and when I put them in, they actually perform like this. I'm not going to call any brand names, but the newer tubes actually had the types of cathode currents that these two do rather than these. These test very strong. So there you go. You can draw your own conclusions and decide which way you want to run it. I don't think it. Well, let's do something here. Let's run it at a bit less power, maybe like 8 watts. If we're running it fairly low, 8 watts would be 8 volts cross 8 ohms. So let's set the voltage up there to 8. It's hard to get it right on. We'll leave it right there. 1.9% distortion is not good. Not good. A lot of harmonics there. And if I go back to the original design voltage, bias voltage, drops off way down. We still got our 8 watts at 0.3%. That's with our weaker tubes. Now let's go to the right channel, our stronger tubes. Well, we got a little bit more output, so let's run it back down to 8 volts. We're kind of measuring the same thing as close as we can. 0.5% distortion. That's at the minus 15. Go to minus 20. We get lower distortion and a tiny bit lower output. So it looks like good strong tubes is the answer. And by the way, we're measuring all this at a kilohertz. Here's our harmonic profile at 8 watts with minus 20. There it is with minus 15. Our second harmonic dropped down, which makes sense for a push-pull amplifier. Our third harmonic came up a bit. So there you go. Hope this helps. I suppose there is one more measurement we should make. What I've done is I have moved the output tubes. These two were over here, and I just moved this one from here to there, and from here to there, and vice versa. So this is our right channel now, which was our best channel. This is our left channel. We've got the best tubes in the left channel. Let's look at this briefly again. Again, I'm going to just be running it at 8 watts. I'm not going to try to go to absolute maximum power at a kilohertz. So there we go, about 8 watts. 8 volts cross 8 ohms would be 8 watts. And right now we're in the minus 15 volt, the original design. And we're on the right channel, which is our weaker tubes. And we've got about 8 watts across 8 ohms at about 0.7% distortion. I go to the minus 15. Okay, here's our harmonic profile. A little bit of second harmonic distortion, not too bad. If we go to the minus 20, goes up quite a bit, doesn't it? Up to 2%. Here's our harmonic profile. That's increased quite a bit. There's at minus 20. There's minus 15. That's with our weak tubes. There's our minus 15. There's minus 20. That was our strong channel a while ago. This is the right channel, but I've moved the output tubes around. So it is following the output tube. Now let's go to the left channel here. And we'll start out at the minus 15, about 8 volts across our 8 ohm load at about 0.7% distortion. There's our harmonic profile. Here's our nice sine wave. Okay, now let's go to minus 20. Distortion increased a little bit. Output dropped slightly. Minus 20. Minus 15. This is on our good tubes, our strongest ones. This is the minus 15. There's the minus 20. Second harmonic went up. That's our increase right here. This increased to 1%. It'll go back to minus 15. That's our second harmonic coming in there. Minus 15. Minus 20. So saying that it performs exactly the same at minus 20 volts, I'm beginning to doubt that, but you can draw your own conclusions. And again, it's going to make the tubes last a bit longer. But I guess that about wraps it up. Hope this helps. Hope you enjoy it.